1, we're in section 5.8 now. This is going to be biology and chemistry. So more like how this stuff is used in the real world. So we're going to be using, let me write the formula out for number 1. It's P of T equals 600 e to the, we are 5.8, 0.02 T, 0.002 T. Yeah, this is section 5.8, biology and chemistry applications. Okay, so there's the formula that they give you. Well, it's the number of insects.
I could give you some chemistry problems that would curl your toes.
Yes.
And they're going to, now Math Excel, let me show you what Math Excel will use. MathExcel.com. They use P equals P0 to the KT throughout this section. And that's totally fine, but I've found that confuses students to change the letters. So I want to let you know, I'm just going to use PERT because it's the same as PERT. They're just calling them by different letters there, which is, I found confusing for students. So it's just PERT. I want to let you know this whole section is just PERT. All the way through 5.8 is just the PERT. We're not going to use the big formula anymore. No more of this one. No more of the P1 plus R over N to the NT. No more of that. Why not? Well, because biological things and chemical things, they grow smoothly. They don't grow in jumps, huh? They grow continuously. Remember, this is the formula for continuous compounding. So money you can grow in jumps or continuously, but biological and chemical things only grow smoothly, continuously. So all we're going to be using is the PERT formula through the whole section. So that's kind of nice. They'll call it, I'm letting you know, they call it by this other name, but it's basically PERT. They're just using different letters. It's the same thing. So I'm just going to use PERT because you're used to PERT, and I think that'd be easy. So here we go. What's their first question? Determine the number of insects at t equals 0. So question A, number of, and this is the number of insects. Number of insects at time 0. Number of insects at time 0. So how do you find the number of insects at time 0?
600 E.
Yeah, you know what? You don't even have to plug anything. You can just grab the 600.
No.
Did you know it's always going to be that number in the front? Why? Because that's like the principal investment, huh? It's the principal number of insects you put in the bank, right? It's always the starting number, whether it be living things or money. Same deal, right? Math doesn't care. Math just runs the numbers. Whether it's dollars or bugs, math just runs the numbers. Getting the idea? So just like with the money problems, the P in the front, that's the money you put in the bank at first, the principal investment. That's the number of insects at the start. By the way, that's why they call it P0 in a ton, pretty much in all sciences, biology, chemistry, physics, all of them. They'll put letters with a sub-0. You'll see that if you take those, maybe you already have. That means the whatever, in this case population, at time 0. That little 0 means at time 0, meaning at the start, initially. That's what they always do. Whenever in any biology, chemistry, physics formula, they put a little sub-0 next to something. That means it's the whatever, the P, the population, at time 0, meaning it's the start. So it's just the 600, just the number in the front. Next, B, what is the growth rate? They're just seeing if we can read the formula well. So how fast are these buggy boys growing? What is the growth rate?
2%.
Exactly. It's just right here, huh? Yeah. This right here is the R, because remember, it's just PERT. So the R is just what's next to T. So the R is it's just 0.02. But they want us to make it a percentage. So 0.02, change that to 2%, right? The decimal moves 2 places. It's 2%. So you can just read right off the formula. The starting amount of insects is 600. The growth rate is 2%. That means 2%. And what's time here? Time is days. So that means every day there's going to be 2% more insects. That's how fast they're growing. 2% more, 2% more, 2% more. We had a couple months ago, near the end of summer, they seemed like they were growing. Every time I'd go out to the garage at night, open the door, there'd be cockroaches run all over the garage floor, you know. And my wife and kids were concerned. But I thought, they run away as soon as you turn that light on. They're gone. They're not a problem. You can get what you need and you're back out of there.
You see, there's like a
They're like, Dad, can't we spray it? All the neighbors, I see the bug guys, at all the neighbors' house.
at your house.
Exactly. And they all run to our house. So finally I'm like, but how much is it? I'm just cheap people. I mean, I think I understand the economics of 5 children on one income. So my Dad, you won't pay for the bug guy? Well, you want to pay for the bug guy? How much is it? And so eventually I went, all right. Once they were like in my daughter's ceiling, I said, all right, call the bug guy. Well, I'll pay for the bug guy. So would you say something, Doug?
No.
Oh, okay. All right. Question C. So they're growing 2%. Now, how many after 10 days? Question C. How many buggy boys? How many after 10 days? How many after 10 days? So what are we going to do? Find out how many bugs, how many insects after 10 days.
The T would be 10.
Yep, just plug in 10 for the T. Time is 10. So the population of bugs, insects, going to be 600 e to the 0.02 times 10. 10 will go right there, and just hit the buttons on your calculator.
That's kind of scary.
600 times e. The e is above the natural log, right? Hit second natural log. I'm getting 732.8. I don't know, the one around the whole number.
0.8 of a bug.
Yeah, whole number.
Okay.
When you chop them, there's like a 0.8 of a bug.
Right. Yeah.
733. That's why I tried reasoning with my kids. You're stronger than them. 733. What's that?
It's going to take that answer.
700.
Yeah, they want a whole number on this
You
one.
can't round up a living creature.
Right, that's true. Remember, the math is just estimating.
Okay.
Yeah, they want a whole number.
All right.
Yeah. But yeah, so it's all just estimating. Math is just estimating. There isn't going to be exactly 733 bugs. It's 750, 720, something in that
They
neighborhood.
say that
Some are gonna
the
die.
average family is
Some are going to have a little more.
a
than
mom and dad and 2.3 kids.
Right,
Yeah.
0.3 of a kid. All right.
that. Average.
When will the insect population reach 900? Okay, let's answer that. When is the population 900? Let me bring over the formula. A equals 600 e to the 0.02 t, right? So how we can find that? When they're going to be 900
We're
bugs?
looking for 2.
So what are we going to do to solve that question?
Get it get the E with the exponent.
Yeah, where do we put the 900? When I called it A, I think they called it P. Whatever, it goes in the front, huh? The 900 goes in the front. It's the amount of bugs later, the population of insects. So yeah, you just got to take that now and solve for T. They said when, which means we need T, we need number of days, time. So can you solve that? So what are you going to do to solve for T? Where's T? In the power. So remember what we learned? When letters up in the power zone, you're going to get the base alone and L in both sides, right? Got those two differences? Yeah.
Should you
Becca?
reduce that fraction or no?
Yeah, I would. It's 1.5. It's real clean.
Finally.
So divide by 600 on both sides. So we get 1.5. Yeah, I do. Becca, your question is a good one. If the fraction was really ugly, came out like a decimal that goes forever, I would have left it. But if it comes out a fraction that ends, then I go ahead and do it. Just easier that way. All right, and so now we L in both sides. So you get the base alone. So whenever we have a letter in the power zone, right? Getting the hang of this, letter in the power zone, get the base alone and L in both sides. And the power drops down. So we get 0.02 T, L and E, which is just 1, right? That's convenient. The L and E is just 1. The power drops down. Everybody see that? The whole power comes down. That's the great thing about logs. That third quality of logs, powers come down. And how do we get T alone? Divide by 0.02. And T's alone, hit the buttons on your calculator. T equals 20.27. That's days, huh? I don't know how far there was. 10th, okay, so 20.3 days. 20 days till 900 bugs. So that's how they chart, growth of anything in biology. Okay, so let's do E. When will it double? That's a good question. Oh, no, we could do that. Let's move on. So number 2. So strontium 90, something about it. It's a radioactive decays. Decays according to A equals A0 e to the minus 0.0244 t. 0.0244 t. And scientist has 800 at the start. At the start, there's 800 grams. Okay, so first off, before I give you an actual question, they're talking about decay now. Decay. So that means it's going away. So now, the other ones we've been doing, everything we've been doing up to now has been growing. The money was growing, the costs of college were growing, the insect population was growing. Now this one's decay. Notice you have a lump of that strontium 90. You have 800 grams of that stuff, and over time, it goes out into the atmosphere, and the pile shrinks slowly over time. It decays. It gets smaller and smaller and smaller over time, so it's going out into the atmosphere. So how do we know right from the math formula that it's going down instead of up? What tells us that in the math formula? Yeah, the negative right there. Negative rate means it's decaying. It's shrinking. Right, so negative rates mean it's shrinking, it's going down. So, right, the other ones we did to like the insects, we go back, the insect, see it was positive 0.02 up there? See how it was positive? So the insects were not decaying, they were growing. Okay, so that's all it takes. When you have a negative on the rate, things shrink. If you have a positive on the rate, they grow. Okay, so this is the decay problem. This substance, strontium 90, is decaying. It's going away. Now, here come their questions. What is the decay rate? So, question A. What is the decay rate?
2.44%.
Yeah, it's just right there again. Just remember, it's just PERT. All these formulas are just PERT. So there's the R right there. Minus 0.0244. We've got to move it twice to make it a percentage.
Yeah.
Minus 2.44%. Question B. How much after 30 years? These are years now, not days. 30 years. So how much strontium 90 is left after 30? If you leave that lump sitting on the shelf for 30 years, it'll decay. How much will be left? So what do? Going to use the formula. What's the A sub 0?
That's when it starts at, right?
Yeah, again, the sub 0 is always at time 0. That's the amount at time 0, the amount at the start. And what is the amount at the start?
800.
Yeah, they told us 800. Is that good there? That's 800. That's like the principal, huh? The number in the front of the E is just like the principal investment in money, economic problems. And the T is 30 years. So that strontium should be lower. You should get a number lower than 800 because it's decaying. I'm getting 384. I don't know how far they want me to round. It says, round whole number. So I get 384.7. They want me to round to 385 grams.
That's an exact measure.
385 grams. So it's gone down a lot, huh? Went from 800 grams, it's less than half of what it was. It's down under 400. It's 385 grams after 30 years. Good? Questions on that? We have a couple more questions on this one. So now, how are we doing? We got 20 minutes left. You guys hanging in there? Are you still absorbing math news? Let's jump down to D. I'll skip C. C would be easy for you. Let's jump to D.
Yeah, no, it's not simple.
They're going to say, what's the half-life of the strontium? 90. Don't worry about the 90 is just part of the name. You don't have to do anything with the 90. So what's the half-life? Remember the formula again. It's A equals 800 e to the minus 0.0244 t. Yeah. Okay. Yeah, what's the half-life?
You have to use half-life.
Good. Yes, exactly. Yeah, it's just like for the money problems when we talked about doubling, right? Because money was growing. We said how long till the money doubles? We would plug in, twice as much money. Now, how long half-life means how long till there's half left. Exactly. So that would be, what am I going to put in for A?
400.
Yeah, because there's 800 originally. So for half to be left, I'm going to put in 400. Exactly. Is that good to there? So half-life means how long till half. How long until half left. That's what half-life means.
And we can just reduce that to 0.5, right?
Yeah, right. Yeah, so what do we do to solve? For we got T up there in the power zone, huh? So we're going to get the base alone and L in both sides again, right? So divide by that 800. And we get 0.5 is e to the minus 0.0244 t. And then we get rid of that, we bring the power down by ln on both sides. Good there. So bring the whole power down, and ln of e, that's just 1, isn't it? That's just gone. How do we finish solving for t?
Divide.
Just divide by minus 0.0244. I'm getting 28.408. I don't know how far they want me to round. They say round to the 10th. So that'd be 28.4 years. 28.4 years, half of it will be gone. That fits with our last answer. We found out in 30 years that more than half is gone, huh? So in just under 30 years, half will be gone. Sure enough, 28.4 years. Good on that? Good with the half-life? Questions I can answer on that? Okay. Measure all these kind of growing things. So, all right. So I'm going to use the PERT formula. Every problem in this biology, chemistry section is with the PERT formula because living things grow smoothly. So, all right. So the population of the city doubles in 26 months. Current population is 10,000. Final population in 5 years. Okay. So we did. Yeah. So what are we going to do with the 10,000 first off?
It's going to be in front.
Yeah, that's the current. That's the starting. Right now it's 10,000. How much later? The 10,000 is the now. So the 10,000 is the now. And we want to find out. Oh, and what is the A? If we want it to double.
20,000.
20,000. Is that good? And the T.
5 years.
Well,
It's going to be that many months, not years, right?
yeah, we're going to have to get the two time units to be the same, aren't we? See how they're, yeah, good eye. They're talking about months and years, and we can't have a changing of the time. So we got to get them both in months or both in years. You can do it either way. It'll work fine either way. I think it might be easier just to take this and go 5 times 12, 60 months. Just change, because otherwise you have a decimal. I don't want decimals. So let's just get them all in months. You could get them all in years, though. That would work out fine, too. Either way will be fine. I'm just going to get them all in months. So 60 months. So 5 times 12, 60 months. Is that good? So it's almost, yeah.
So to find the rate, we have to.
Yeah. Let me explain. So here they're going to get hard. So yes, everybody caught up to here. I want to explain. I'm going to actually have a whole like 2-phase process to help you. These get a little more complex. This is right what we're on right now. The other stuff was kind of like warm up. This is the main dish, right? This is the main. What we're about to do is the main thing we'll do on like 5 problems in this section. It's the main thing. So everybody good to hear so far? So we said the population doubles. So it goes 10,000 was the start. Right? That's the current is 10,000. It starts at 10,000. It doubles, so it becomes 20,000 when time becomes 26 months. In 26 months, the population doubles. Now, they're saying how much in 5 years, 60 months. So what you have to do on these is first off, you have to find the e to the r right there. And that's weird because normally I would say find r, wouldn't I? But I'm going to make it, I'm doing this to make it easier. So, and the Math Excel does exactly the same thing. It's a good plan. First, find e to the r. And then after we find e to the r, second, after we do that, then we'll finish the problem with the last bit of information. That's how we're always going to do these more difficult ones. First, find the e to the r. So, okay, how am I going to, in fact, let me move that up and get it out of the way. How am I going to find, so first, find e to the r. How am I going to find e to the r? Well, let's divide by that 10,000, huh? That's for sure a good move. Boom, that's 2 equals e to the r times 26. Good so far?
126 both sides.
Exactly, yeah. Because we want e to the r, don't we? See what we want? I want to get this piece right here alone. This is where it could be confusing because, you know, I can see where you would think, well, Mr. You got on the board right now and you wrote out earlier, right back here, you wrote, I don't know if I can find it now. It's back a ways. No, it's not going back, whatever. You remember I wrote out earlier and I said if you have the letter in the power zone, you want to LN. It's only if you have a number that you do the 1 over the number. Well, it's because I don't want to get rid of that letter in the power zone. It's because I'm not trying to get the whole thing down. I'm trying to find e to the r. I want to leave the r up there. Do you get it? I want to leave it up now. Even why? Why are you doing it? Well, it's just because it's simply easier. You'll see as it plays out, it's just simpler to do it this way. So so if I want to leave the r up there, I don't want to ln, because then the whole power would come down, the 26 and the r. Don't want that. Want to leave the r up there, right? So if I want to leave the r up there and I only want to get rid of the 26.
Square root both sides. Like 6.
Well, that's the 1 over 26 is the same as square rooting 26. Yeah, effectively, yes. So I just do the number thing because I only want to get rid of the number. Make sense? I want to leave the r up there. That's why I don't ln. You think, yeah, but you got a letter. You said when there's a letter. When there's a letter that I want to get down, I want to leave that letter up there. So I just get rid of the number. So what do we get then? 2 to the 1 over 26 is e to the r. So I was able to get e to the r. Right? These 26's cancel. Now, why am I doing all that? Well, because now that you've done that, that'll make it so much nicer as you do part 2 now. Part 2, you come in for part 2 and you say, okay, a equals pert. It's all about pert. And now I know what the e to the r is. What is e to the r? 2 to the 126. And what's the p? That's 10,000 still. e to the r to the t. Does that make sense? I just put in the e to the r right there. Everybody tracking with me? So I put in the e to the r right there. 2 to the 126. Now we can finish the problem. So the first part is you find the e. We can do this on all these. First part, you find the e to the r. Second part, you finish the problem. So you put in the e to the r. How do we finish now? 5 years. They want the population in 5 years or 60 months. So I grab that 60 and I put it in right there. So the amount is going to be 10,000. 2 to the 126 times the power is 60 up there, huh? So hit the buttons on your calculator. I'm getting the wrong answer. I did something wrong. Wonder why. Anyway, I got it. So it's 49,509. So the population grows from 10,000 to almost 50,000 in 5 years.
Exponential bits.
It is. So that makes sense on what we did there. So let's try it again. It's going to be pretty much the same thing on these. That is 2 phases. First, you get e to the r. Second, you plug in the e to the r and the last bit of information and get your answer. So that's kind of interesting, huh? Just from knowing how long it takes the population to double, we're able to get a feel of the rate, get the e to the r, and with that rate knowledge, figure out anything they want to know from there. How much it'll grow in 5 years. Okay. So half-life of radium is 1690 years.
No, just one. Just one.
Half-life of radium,
Half-life of radium.
1690 years. How much in 490? Oh, it starts 80 grams now. 80 grams now. How much left in 490 years? So the half-life of radium is 1690 years, 80 grams now. How much left in 490 years?
Wouldn't you want to find out how much 490 is of 1690?
Well, there's probably a method you could do that way. So what I'm going to do, so you know the formula we're going to use? A whole section, PERT, right? So living things, grow and decay, chemicals, continuously. So we always use PERT. Okay. Now, what do we do with the half-life of the radium is 1690 years? Remember what half-life means?
-50.
Yeah, that means, after 1,690 years, half of it's left. So that's why there's problems with radioactive things. They last forever, right? They don't go away. So that's what that means. So that radium stuff, if you have 80 grams now, that means 1,690 years later, it'll be down to 40 grams. Then 1,690 years later, it'll be down to 20. And then 10, and then 5, and then 2.5, and then just half, every 1,690 years. Half of it goes away. Okay, so with that in mind, let me tell you 2 things. Number 1, I'm going to do a derivation, and we're going to end up with a quick little shortcut formula. Let me just give you the shortcut formula, and then I'll derive it afterwards. Here's the shortcut. Whenever you read a problem and they tell you the half-life, you can just automatically go, oh, okay. Then it's just going to be 0.5, that's the half, to the t over whatever that half-life is. So in other words, in this problem, it's going to be p 0.5, that's the half, T over 1690. And then you just plug in and you're done. So that will be a shortcut formula we always use for half-life problems. So let's just finish this problem, and with whatever time we have left, I'll tell you where I got that shortcut from. So if we know that, if we're like, oh, so that's all you got to do for half-life problems, that is, it's just 0.5 to the T over the half-life, 1690. Just grab the, what's the P? The amount now? And what's that? 80? 80 is, it's like the principal investment, the amount you put in the bank first, the amount of radium that's there first, times 0.5 to the T. What's the time? 490 years. Over the 16. This is kind of like what you were saying, Renee, about dividing, getting that portion. This is how you would do that. Yeah. So you're right. Yeah, that's exactly right. And this is 490 divided by 1690 times 80. So I'm getting the amount will be 65.43, however far they want us to round, I don't know, grams left after 490 years. So we have 2 minutes. I can show you how I derive that. But is that good? That'd be the final answer to that question. Does that make sense? Now, where'd that formula come from? It's really pretty easy. I just did phase 1, basically. Just come over here and do the first thing where you want to find e to the r, right? So let's find e to the r. Amount equals 80 e to the r times t. And they're telling me the half-life, how long till half, is 1690 years. So that means the amount will be half the original. What's that? What's half the original? 40. When the time is 1690, huh? I'm just showing you where I came up with this handy-dandy formula. So then how would you solve that? You would divide by the 80. Guess what 40 over 80 is? You know. 0.5 e to the r times 1690. Now how do you get rid of that? You want to keep the e, you want e to the r, you want to just get rid of the 1690, so what do? 1 over 1690. 1 over 1690 cancels out. So e to the r is 1 over 1690. I'm kind of running out of room here. So let me just come up here. So, whoops, I erased the t. So coming up here. So then the formula, which is a equals 80e, or just p, I'll just put p e to the rt. So now this is p e to the r. What's e to the r? This. 0.5 to 1 over 1690 times t. Just see and that t just goes to the top because it's t over 1. There's the half-life formula, you say? That's where that comes from. It's just going to be 0.5 to the t over the half-life. So any half-life problem, you can just start right. If you put that in your 3x5 card, just use that, zip them out.
I wish chemistry was that
Half-life.
simple.
All